Welcome to the Sustainable City, and I'm delighted you're able to join me to be an energy engineer for a day with Heriot-Watt University. Why have I started here in Sustainable City? Well, obviously, one of the larger challenges that are facing you and me and future generations will be to develop a more sustainable future. And part of that, of course, will be in the integration of renewable energy or sources of renewable energy into our energy mix. Sustainable City is a great example in how we develop communities to reduce, first of all, our energy needs, but also how we integrate renewables into everything that we do. So solar, which is one of the more prevalent forms of renewable energy resources here in Dubai, here in the UAE, is something that is becoming a much larger part of the energy mix. And it's done in different ways. So we can look at solar, and you may be familiar with these large-scale solar, ground-mounted solar plants that are on the megawatt and potentially even gigawatt scales, contributing directly into our grid. And it is what is powering our day-to-day lives. However, in Sustainable City, we're integrating renewables on smaller scales into everything that we do. So as we pan across, and as you will see on my right-hand side, that we have solar integrated into our car parks. Underneath here, we're generating quite a lot of energy for individuals, but also for the community. And as you look up on the tops of the dwellings and the villas here, they're also generating electricity that ensures that your domestic activity is having a carbon footprint, again, about half of what would be typical in the region. Now, how we do that is today's task. So we will be looking at all the factors that go into making a very good design, making sure that we are designing energy or renewable energy resources that can best support a more sustainable future. So one of the roles of an energy engineer will be in the design of renewable energy systems. And here in Dubai and in Sustainable City, one of the largest forms of renewable energy, of course, is solar. As you can see over my right-hand side here, we have a relatively large community-scale solar energy system. And its design is what we're going to concern ourselves with today. Although you will choose your own location, which will inevitably mean it'll operate in different environmental conditions, and also perhaps for a different purpose, for a community like Sustainable City, or maybe for an individual dwelling that's on or off-grid, maybe in an urban or more rural environment. All of that will be your choice. The challenges and the things that need to be considered as an energy engineer are the same. So there are some technical challenges to start with. Where in the world am I going to position my renewable energy system? A solar panel, should it be directed north, south, east, or west? What orientation would give me the best outcome? On top of that, you might want to consider the tilt of the panel. Should it be more biased towards a summer orientation where it's a little bit flatter, or more vertical, giving you more energy potentially when you need it in the winter months? All of these are important technical factors that influence the ultimate design of your system. But there may be a few other things you want to consider. Some very operational things. Did you know, for example, that the conversion efficiency of a solar panel goes down as the temperature goes up? And that really influences the overall potential performance of your system. And ultimately, a solar panel is a black body in the sun. It will get hot. So we are, in operation, going to compromise its conversion efficiency. Perhaps there's potential to use the ambient air and the wind to maintain or to keep its temperature as low as possible so that it is converting or generating as much energy when we need it. On top of that, one of the big environmental concerns here will be dusting. Here in the UAE, there tends to be quite a lot of dust that accumulates on the surfaces of our solar panels. And as that does happen, it'll either reflect or it'll certainly stop the panel absorbing solar energy, reducing its potential to generate electricity. So all of these become factors that you can be, first of all, aware of, and then to try to design around. Before we get on with today's task, I want you to consider what makes a good design. Is it the most efficient design? Very likely. Is it the one that costs the least? Potentially. Over its full lifetime will be important as well. We want it to last quite a long time because we're investing a lot of money in its installation in the first place. Another thing I'd like you to at least consider is, when does it generate energy? One of the roles of an energy engineer would be to best match the demand with the supply. So here in a domestic or in a community scale development, you'll often find there is a mismatch. Solar obviously peaks in the middle of the day. That's probably when you're going to get the most energy. But the demand for energy is often in the mornings before we go to school and work, and in the evenings when we return to our homes and maybe watch some television or do some cooking. So that mismatch might be something to consider. If we're grid connected, we can maybe export energy during the day and then import it back in the evenings. Is there a cost associated with that? Or do we have a battery? Do we invest in some battery technology so that we can harness our own energy, store it, and then release it for when we need it the next evening, the next day? All of those are elements we'd like you to consider in your design. So with that, let's get on with the task. Before we design our renewable energy system with our solar photovoltaic panels, we're going to look at some of the environmental aspects and the configuration of the design that might affect its ultimate performance and the amount of energy that it will yield. So what we've done is set up a small experiment. What I have here is a small photovoltaic panel, and we've connected it to our computer so we can measure the amount of output, the amount of energy it's producing at any particular time. And that's the red line that's passing across the screen there. What I have here is a little lamp, and this is going to represent our sun. It's going to be our renewable energy source. And if I turn on the lamp and point it towards the panel, you will see the line sharply goes up. So we can see that it's working. It's responding quite well to our solar simulator here. Now, what we want to look at is what would happen as the sun passes across the sky. So from sunrise, passing across the panel during the day to sunset. So again, I'm going to turn on the panel and I'm going to direct it away from the panel. First of all, small increase there, just due to reflections. And then as we pass across the sky, getting closer and closer, sun is rising, passing across the panel, you'll see the little peak. This is when it's directly pointed at the panel, which would typically be at solar noon, midday, and then decrease again as we go into the evening and eventually sunset. So this introduces a certain amount of variability into the energy yield from our solar panel. And this all will factor into your design, because when your panel is generating energy is as important to how much energy it is generating. Ideally, we would like to have that energy when we want to use it, because if it's generating more energy, maybe during the middle of the day when nobody is home, then we either need to store it or feed it into the grid and then buy it back later when we need it in the evening. Now, another thing to consider when we are designing a system, quite a simple system, or what looks like a simple system, is shading. So again, if I point my solar resource, point the sun towards my panel, I can see that I'm getting my maximum output there. But imagine this panel is in a built-up urban environment. And depending on the time of the year and the time of the day, it's going to cast different shadows just because of the building nearby, or because even people are moving or walking past. Now, I'm going to simulate that shading with just this thing here that's going to block part of the panel. Depending on how I block the panel, I will influence its yield. So in this vertical orientation here, you've seen that the output has dropped quite significantly. If, however, I block it on the horizontal, I'm blocking approximately the same area, but it hasn't had nearly as much effect. So the orientation of your panel is very important as well. And the partial shading or the partial illumination of the panel will affect its ultimate yield. Why does that happen, you might ask? Well, really it has to do with the electrical configuration of the panel. So in certain configurations, as the cells all go together in a string, you are current limiting the panel. That means that the part that is shaded is reducing the overall current flowing through the circuit across the whole of the panel. So how you design a panel and how you configure all the cells together that make one big system is an important factor to consider. We use a device called a Heliodom to investigate the pathway of the sun across the sky and how it interacts with our built environment. So for this, we have 3D printed a small version of the Burj Al Arab. And I can turn on lights successively, like this, to show and investigate the shading or shadowing that is created as the sun passes across the sky from morning up to solar noon, midday. Now that's a winter orientation where the sun passes at an angle like this across the sky. In the summer months, however, we can adjust it to be in a much more vertical orientation. And now you can see the difference to the shading and also the angle of incidence. That's the angle that the sun makes with the surface of the building, but also the surface of solar panels that might be located in that area. Now those angles and that shadowing are two very important factors that need to be considered in your overall solar energy design. So to actually design our renewable energy system, we're going to use a pretty sophisticated piece of software that's provided by NREL. That's the National Renewable Energy Laboratory. And it's called PV-Watts Calculator. And you can access it by going to pvwatts.nrel.gov. Now the first thing it asks you for is your location. Well, not necessarily your location, but the location where you want to design your renewable energy system. So what I've done here, in get started, I've typed in Dubai, and I'm going to press go. And what it's doing there is it is identifying the nearest source of solar resource data. And as you can see here, it has found International Abu Dhabi, United Arab Emirates. So that is the international airport in Abu Dhabi. And it says it's 71 miles away, which is just a little over 110 kilometers away from us. So you might say that that's going to enter a little bit of uncertainty into our design, but it's pretty close. It's close enough that the weather or the climate isn't that much different from Dubai to Abu Dhabi. And the weather it's accessing is certainly solar irradiance. It will know the path that the sun translates across the sky, but on top of that, it also understands what we call the TMY, the typical meteorological year, which include, yes, solar irradiance, but also things like ambient temperature, wind speed and direction, and all of those environmental factors that might affect the ultimate performance of your renewable energy system. So that simple choice of your location has a huge influence on the ultimate design that you will end up providing. So our next step then is to scroll down and to just look at the map. And we can say, yes, we're in Dubai. We're going to click this Go button on the right-hand side. And we're going to get a little bit more specific now. By going to this Draw Your System part, it'll open up a map. I'm going to close that and maximize. This just looks like Google Maps. I'm going to zoom out. I'm going to navigate through Dubai, right down here to the campus of Heriot-Watt University, as you can see here. So what I'm proposing to do here is to design a system to provide solar energy, renewable energy for the Heriot-Watt campus in Dubai. And it's pretty simple, our next step. I'm going to take advantage of this whole roof. And by doing so, I'm just going to click 4 times to get the limits of my design. 1, 2, 3, and 4. And it's covering the whole area of the roof. Now, there are some limitations to that. As you can see, there's quite a lot of infrastructure on our roof, so this might not be exactly possible, or if it is, I would have to lift it up and make sure that the panels are covering over all of that equipment. That's probably more to do with the air conditioning systems and services for Heriot-Watt University. Once I'm happy with that, I can minimize and I can click Save. And straight away it's doing a calculation. It's able to scale that area, and it also knows where that is
for us to enter that in as part of our algorithm, as part of our design to predict the ultimate and eventual yield from the renewable energy system. We can now get into it in a little bit more detail. As you can see here, I can size my system. You see that number there, 471.8? That is the predicted size of our system. That's our maximum. Now I can change that, I can reduce it or increase it, but I would want to do so in a way that is consistent with the area that I'm covering. So I'm not going to change it. I've defined that number by choosing my area. I'm then going to choose my module. Now the module is the type of solar panel that we are using. So I can go with standard, I can go with premium, or I can go with thin film. Why not go with premium for now? Seems like an obvious choice. But of course, when you are doing a design, you would also want to be conscious of the economics. How much is that premium panel over a solar panel? And is it worth it? Over its lifetime, is it going to generate so much extra energy that it's going to be worth that extra investment? Let's take a look at that later. We're then going to go to an array type. And there's a few choices here that I can go from. I can go from an open rack, roof mount, one axis tracking, one axis back tracking, or two axis tracking. Now, generally, most solar installations of this type are not going to be tracking. That means they're going to be in fixed orientation at a fixed tilt angle. The sun is going to pass across the sky with irrespective, and they're going to have different angles of incidence, different angles at which the sun is going to interact or impinge upon that surface of the solar panel. I could go for a more sophisticated design, one with two axis tracking, one that tracks across the sky throughout the day and also tilts to compensate for the seasonal change of the sun. But practically, most installations are going to be roof mounted, in this case, with a fixed axis. Now, straight away, it's done some calculations, or it's estimating that my system's losses are going to be 14.08. I would leave that at the default unless you know otherwise. There might be reasons why you would increase or decrease those systems losses. And if ever you're uncertain, just click on the little information button there, and it'll tell you how is it calculating those systems losses and why. So for example, if I scroll down here, you can see that 14.08 is made up of losses due to soiling. So this is allowing for the fact that there might be some dust in the air that's going to land and on average accumulate a total loss of about 2%. As we saw earlier, another 3% is allowed for shading. So maybe one panel is close to another and it's going to shade it, or maybe the building next door at certain times of the year and certain times of the day is going to contribute to some of that shading. There's other things like mismatch, which is an electrical term to do with one cell generating more energy than another and limiting the performance of another. And as you can see there, that's contributing to 2%. And you can go down through it. You can see here, depending on the age at the moment, because they're new, we're saying there's zero losses there, but we could increase that percentage over time as we'd expect the panels to degrade over their lifetime. And typically, there's a good point to maybe say that you could expect a typical life for something like this to be maybe 20, 25 years. So I'm going to close that now. I'm going to now look at the tilt angle. Now, the tilt angle is an interesting one because it's going to define the angle at which the panels interact with the sun. Now, they're fixed, so we have to pick a fixed angle. They're not tracking. And we could go quite flat, which would optimize for the summer months as the sun passes across the sky, quite in a vertical here in Dubai. Or we could go quite nearly vertical, closer to a much higher angle. And that would perhaps optimize for the winter months. And that's a choice that you might make depending on not just how much energy, if you want to maximize the energy, or whether you want to maximize the energy for a particular time of year, perhaps when you need it. And here in Dubai, because one of the major uses of energy here, I think something like 95% of electricity used during the summer months is actually attributed to space and water cooling. I might be more inclined to optimize my panels to be quite flat so that they're going to maximize the amount of energy that they generate during the summer months. So I could even decrease that if I wanted, maybe to 10 degrees. Totally up to you at this stage. And then the azimuth angle has really got to do with how far north or south the panel is orientated. So if I'm looking at the sun passing across the sky, across the southern sky, and I go at 180 degrees, it means I'm going to be perpendicular to that path. If I was at 90 degrees or plus or minus 90 degrees, I would be facing more east or west. So 180 degrees, certainly in the northern hemisphere, is generally considered the correct answer. Now there are some other parameters that we can optimize here. Some electrical ones like the DC to AC ratio. What you may know already is that solar PV panels generate DC, direct current electricity. And in the conversion from DC to AC, there can be some losses there. And you can see here we're allowing for 1.2. Inverter efficiency, about 96%, so 4% loss, just as you convert from DC to AC. And maybe something to consider for the future. Should, in certain circumstances, we keep things as DC and use DC in so many of our day-to-day applications. And then you have ground coverage of 0.4. So ground coverage can vary significantly. You might think, based on the area that I chose there, that 100% of that area is going to be covered by solar panels. And of course, it's not. There will be gaps left between solar panels for good reason. We don't want one solar panel to shade another. Also, there's just simply objects and other infrastructure on our roof. So, funnily enough, a ground coverage ratio of about 0.4 or 40% would be about typical. Again, if this was a ground-mounted site, so a brown or green field, then you could increase that, but unlikely to ever get to 100%. Now, I mentioned earlier that economics will play an important role in any design here. So with that, we can put in our economic factors, and it really is the price at which we pay for energy. Think of it this way. Renewable energy is typically capital intensive. We have to put a lot of money up front, and we expect that investment to last 20 to 25 years. The fuel, on the other hand, is close to free, right? The sun shines, and we're going to take full advantage of that. This is non-typical for other traditional sources of energy, like oil or gas or coal-powered installations. They will have a capital investment, certainly, but you will have to pay for the fuel over the lifetime of the plant. So the economics work out a little bit differently. So in this case, I'm going to choose my rate type. I'm going to go with either commercial or residential. We're commercial, I guess. And based on that, DEWA, or our energy provider, will sell us and we will buy electricity at different prices. Now, it's given in dollars here. I'm going to go with something like 0.08, so that's about 8 US cents per kilowatt hour, which would be very typical, but will vary depending on where you are in the world. Now, all of those parameters are within your control. So as I press the next button, it's going to predict, using the input data of the typical meteorological year, my choice of panels, and it's going to predict how much energy it's going to yield over its lifetime, and it's going to predict how much money we're saving or even generating if you're selling this energy to somebody else. But you can always go back. And it's important that when we look at our data, that we understand the influence of each parameter. So I could perhaps change my land coverage ratio, or I could increase the conversion efficiency, or reduce our losses, or choose a different type of panel. In that way, you're doing a certain amount of iterative design that's going to optimize the overall design and configuration of your renewable energy system. So let's press the next button. And it's doing a bit of computation. What it has here now is it's giving me a breakdown of this typical year. What I can see on the left-hand side of is on a monthly basis from January to December, I have a typical solar radiation. That's how much energy, kilowatt hours per meter squared, 1 meter squared per day. And you can see in January, I'm getting nearly 5, whereas in July, I'm getting about 7.3. That then gets converted into AC energy. So that's electrical energy and AC alternating current. And you can see that that peaks at about 77,550 kilowatt hours. And that's on that's in July. And you can see what the equivalent price then is based on that economic metric I gave of $4,000 in January, and you're either saving or generating the equivalent of $6,203 in July. And that can give you a net total of $65,000 in for a year. Now you can add in some more information here, and then we can do some things like finding installers and all of that. But really what I'm interested in is to look at the data on an hourly basis. So I'm now going to press this button here to download results on an hourly basis into Excel and press OK. Now, this creates a very big spreadsheet. And as I scroll down, you can see what I have here on a month, day, hourly basis. I'm getting the solar irradiance and so much more along the top there, each column giving me more and more information. And what we can see as an example, if we just want to take the AC output of the system, we're getting starting 0. This is obviously in the middle of the night where we're not generating any electricity. And then at sunrise, around 7 o'clock in the morning, I'm beginning to get some AC output. And then as the sun sets, as we're getting to, what is that, 18, 19, so 6, 7 o'clock in the evening in January, my output returns back to 0. And I can see that for every day of the year. So there must be 365 times 24 different lines of output in my Excel spreadsheet here. So data in this form is interesting, but it's not necessarily the easiest thing to interpret. So what I suggest we do is we do a little bit of graphing. Now I'm going to use that to plot. So instead I'm going to insert my plot. And I'm going to put it across the top here. I'm going to add in some data. Select data, add, and on my x-axis, I'm going to choose these hours, and I think I'll go down a few days. So if I go to about 100, let's go down to there, 7 days, that's a week, and choose my y values, back up to the top, get my output down to the end of the 7th day. Somewhere around there. Yep. And press OK. And OK. I can scroll right back up to the top and see my time trace of the output from my renewable energy system. So what you can see from the very beginning here is that we have, well, typical profile here. Nothing at nighttime, obviously. Sun is not up. Peaks in the middle of the day and then decreases again. But you do see on day 2 and day 3 that perhaps the output from my system has been slightly compromised. And this is probably got to do with just the clouding conditions. Particularly on day 3, you can see maybe there was a lot of cloud that day in the middle of the day, and it prevented the sun full intensity from hitting the panel. So this gives us a good view of the operation of our panel. Now your task then would be to analyze this data, maybe go back into the calculator. It's very easy, just press this button here. Change a parameter or two. Maybe you change your location. Maybe you want to change from a premium panel to a standard panel. Maybe you're going to change it from a fixed to a tracking device. Or you're going to do something that would perhaps reduce the system losses. You might want to change that tilt angle back to 20 degrees and see what happens. And in that way, you're going to do this element of iterative design. So just to say, engineers don't do trial and error. What we try to do is understand the trends, understand the effects of system or design parameters on the ultimate performance of the system. So when you change a single parameter like tilt angle, you might want to do that 2 or 3 times, see how that's affecting the overall output at different times of the year, and then make a decision. Should it be 20? Should it be 18? Should it be 25? Should it be 30? Totally up to you what you want to do here. We're really interested to see your designs. So after that, take a screenshot of something like this. See if my yield is higher or lower. See if my profitability or the amount of energy or amount of money I'm going to make from my system is higher or lower. And then post your results.
So now we get to the good part, the fun stuff, the experimental testing. We've done our design, and for me, I designed a solar energy system for the roof of Heriot-Watt University in Dubai. So that's where I find myself at 8:40 in the morning on the 18th of March. And why is it important to know that? Well, it's important because that defines the location of the sun in the sky. And on the 18th of March, I can tell you that the sun rose at 6:25 this morning, a little over 2 hours ago, at 91 degrees east. And I can also tell you that it is expected to set at 18:28 this evening, so just before 6:30 at 269 degrees west. So we can then tell that the sun is going to take this path across the sky. Knowing that, we've set up our solar panel, a very small solar panel, solar cell here, facing due south and at an angle here of about 45 degrees. So we will log the data, we will measure how much energy it is converting from the sun throughout the day. And it's set up with a time lapse here on our GoPro, so we'll be able to time lapse that testing throughout the day. And the best way of understanding that time lapse will be to track the shadow that's cast by our setup here. Now, we also have set up a pyranometer, and a pyranometer is an irradiance meter. It measures the intensity of the sun as it hits this surface. So we will be able to cross-reference the yields, the energy that has been generated by the solar panel with the environmental conditions, with the strength of the sun in the sky. And that may vary throughout the day. Today is a little bit hazy, there's a little bit of cloud in the sky, so we'll be able to do that cross-referencing between what the sun potential is and what our solar panel is producing. So we'll check back later to see how this experiment goes.
So it's about midday now, and you can tell from the shade, the sun is right in the middle of the sky, slightly to the outside because of the season, but this is the best as it gets. Now the solar panel here is facing the sun directly and harvesting most of that solar radiation. The weather is cool today, a bit windy, and that's good for the panel because that keeps the temperature of the panel down. Temperature affects the efficiency in a direct way. The more the temperature rise of the panel, the less energy you get out of it. That's because of the construction of the semiconductor material on the panel. So it's very important to keep the panels cool. In reality, you have little control on that, but again, allowing wind to move around the panel is a good idea. Now, let's talk about the solar radiation and the shade, which I started with. Shading is something else that we consider when we talk about panels, solar panels, their design and orientation. In particular, partial shading, like what I'm doing now. So I'm shading like half of the solar panel. And you would say, okay, shading half of the panel, then does that mean we get half of the energy? Well, we are going to lose some of the energy. It's not that straightforward because this is partial shading. So half of the panel is working, the other half is struggling to stay up to the limit and the expectation of the system around it. So this is something we consider when we decide where to keep the solar panels. Are there any trees, for example, other panels shading them, or building shading around? And that gets into all our calculation. I'm trying to keep my hand on it so we can see later how that affects the voltage and the current we are logging. Remember, voltage and current are like, the two faces of the same coin. That's power. In order to get your power to the system, you really need a good voltage at a certain level and a good flow of current. Shading affects the flow of current and as a result, you get less power than what's expected. That also applies to temperature. When the temperature rises of the panel, that reduces the power you get out of it. So all in one, lots of engineering go into this field. The good thing that we can see the sun and shine the full day, and we can all play around with these parameters to get to the best out of this setup.
Now we're going to take a look at some of the data that we've acquired from our experiment on the roof. What I've plotted along the x-axis here essentially is a timeline. So it goes from midnight throughout the day to midnight that following evening. And on the y-axis, I'm going to plot the voltage. This is the open circuit voltage from our solar panel. And it's essentially an indication of the amount of energy that that panel might generate for us. And on the right-hand vertical, I have the solar irradiance, which essentially is the DNI, or how intense the solar is from the sun as it passes across the sky. Lots of a time lapse here of the sun as it passes. So let's play this. You might just be able to see early in the morning, 2:30, 3 o'clock, 4 o'clock, very little output. It is, after all, dark. Then come sunrise, which must be around 5 o'clock, we're getting a sharp increase in both solar irradiance and output from the panel. What's happening here, do you think, Mohammed? I see you come into frame.
Yeah. Well, I was trying to check on the shading effect on the panel, and if I shade part of it, all of it, what happens. And I think that drop in there is basically because I'm shading half of the panel. And that's important to understand at the design stage, to plan where to keep your panels, if there are trees or things around, or even if there is cloud coverage during the day, what will happen.
Or if there's a Heriot-Watt engineer walking about your solar panels.
Yeah.
Let's keep going with the simulation or with the data. So now it's dropping, and as you can see, the voltage has dropped like a stone at about 5:30, which is very close to sunset, and then obviously zero afterwards. Couple things now to look at that data. First of all, while it's risen, I'm looking at the voltage output here, Mohammed, it's not perfectly flat. So there's a little bit of jitter other than your interference around midday. What else is going on there, do you think?
Well, I think a number of factors. Sometimes if you have some clouds moving around, dust coverage or anything like reducing how much solar energy you are getting, that's part of it. Other thing is important to understand is reflections from around the panel and how that gets into the picture.
Another thing to look for then is, it might seem strange, why is there more output from our solar panel at 5 or 6 in the morning before the sun has actually gotten up to its full intensity at midday? Well, that's pretty much to do with the measurement that we use, right? So we're using a pyranometer here, which essentially measures DNI, direct normal irradiance. So how much of that sun is actually perpendicular to the sensor? And in the early hours, of course, the sun is coming in at oblique angles. And these panels are clearly getting better and better at accepting that solar, even in early mornings when it's coming in at an oblique angle. So it's reacting very quick and generating energy from you as soon as the sun rises, in this case, just after 5 in the morning. And it continues through solar noon and then drops as the sun sets at about 5:30. Okay, so these are many of the factors that energy engineers have to take into consideration as they design and optimize renewable energy systems. I hope you've had some insights now into some of the challenges and opportunities there are to be an energy engineer, and how important the role is to creating a more sustainable future for everybody.